Life is a series of thousands of miracles. Speaking of series, I'm looking at 16-bit arithmetic at the moment, and the reason for that is that I have a PFS 154 craze going on, and the PFS 154, an 8-bit microcontroller, can do 11-bit PWM, 3 channels of them actually, which we've seen before, so I'll link that up to that continuing project. I'd like to write that in assembler, and I need to know how to do 16-bit, to cover the 11-bit anyway, how to do 16-bit arithmetic in assembler on an 8-bit microcontroller. So yeah, continuing that series, we could just use, for instance, there are some instruction sets in AVR that have, for instance, something like mulls or mull, which means multiplication, so that's the code. And very straightforward then to be doing that. But the ATiny 13 doesn't, and I'm not really sure about the PFS 154. So I don't know, but anyway, I'm just going to learn how to do it via the old-fashioned way. So I'm really old-fashioned, I guess, is to do it decimal. So if we look at decimal, let's say 27 by 58, then we use an algorithm that just is like 7 8s are 56, carry the 5, 7 5s are 35, and that 5 adds up to 40. Now we're not multiplying by 2, we're multiplying by 20, so we put a 0 there. 2 8s are 16 and carry the 1, and 2 5s are 10, and that 1 gives us 11. And then if we add those together, we end up with 6, a 6, a 5, and a 1. No problem. Now, if I was to do that on an AVR simulator, for instance, which we'll do, we'll see what this looks like, we end up getting 3A, representing 58, we end up getting 1B representing 27, and if it all works out, the 1566 should be 061E. How do I know that? Well, 1566 in binary is 110000, and then I think we've got 11110. So there's your 1566, and we can split that up. We can say, okay, if we're looking at hexadecimal, put an extra 0 on end just for fun, then this is an E, this is a 1, and this is a 6. Okay, so 61E. All right, so now let's look at how do we do binary multiplication. So what we'll do is, I guess we'll represent 58 as a binary number. So that's going to be 1, hope I've got enough room here, 111010. And then 27 would be 11011. So that's what we're multiplying. And we'll use the same algorithm. Now, there are other ways of doing this, but what I want to do for my own brain really is to do this as this sort of decimal algorithm and then represent that in assembler as well, and have a look for some. What I'll do is I'll put some I guess decimal and then also hexadecimal representations along the way, so as I'm doing the calculations I can see what's going on. That's the theory anyway. So let's use the same algorithm. So I've got 1 times 0, 1 times 1, and so forth. All I'm going to get here is the same number, so I'm going to get that in the first row. So that's 1 times the 58 up there, if you like. And then, okay, so we add a 0. So we're now multiplying by the 2 times. So then that's going to be also 0, 1, 0, 1, 1, 1. Then we've got 3 zeros. No, we've got 2 zeros. I'm going to better keep track of those. So this is our 10. This is our 20, or in this case, it's going to be 2 and 4. And then we're going to go, what are we up to? Oh, this is all going to be zeros. Okay, so 1, 2, 3, 4, 5, 6. And then we've got 1, 2, 3. And then we've got 1 times this again. So this is going to be 0, 1, 0, 1, 1, 1. And then we'll have 1, 2, 3, 4. Followed by 0, 1, 0, 1, 1, and 1. Well, just making it in time. Okay, nice. might run out of space here, so I might scrunch this up, see how we go. All those zeros are cool. That's a 1, so that's a cool. I'll just scrunch it that way a little bit, don't panic. That's also a 1, so that's fine. That's also a 1, so that's nice. And then we've got a 1, a 1, and a 1, so that's 3. So that's going to give us a 1 with a 1 left over. And then we've got 1, 2, 3, 4. 4 is 0, 0, 1, so that's going to be a 0 and a 1. And then we've got 1 and 1, which is 2, so that's a 0 and a 1. Then we've got 1, 2, 3, 4, which is a 0, and a 1. And then we've got 1 and 1 is 2, which is a 0 and a 1. And now we see the point of the scrunching, and I've got 1 and 1, which is 3. So that's 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So that is exactly the same. So now we've got, that's our E, and that's our 1, and that's our 6. Okay, phase 1 complete. Now all I want to do is find out what all this represents in decimal and what it all represents in hexadecimal, and then we can simulate it and see if I can get it in assembler as well. Alright, so I want to keep track of this. Let's go with decimal first. So we know that this is 58, and we know that this is 27. Then we've got 1 times 58, so this one comes out to be 58. Then we move that to the left, and it ends up being 116. This one is just 0. We move this one to the left, so it's now moving it to the left twice. So that becomes 464. And then move it to the left once more, which is 928. So if we add up 58, 116, 0, 464, and 928, we get 1566. But we won't see any of that on the actual simulator. And it would also be useful to see what happens along the way. So when we just add, let's say, these two together, then we're going to end up getting out a 174, and then adding 174 to 0 should give us a 174, a 174 and a 468 gives us a 638, and then a 638 and a 928 is the final answer. Okay, that's great, but what are we going to see? Well, 58 is going to be 3A, and then 27 is going to be a 1B, and then our first counting should give us our 58. So that's our 3A. Alrighty, good. And then when we shift to get the 116, that's going to be 74 in hexadecimal. And then 3A plus 74 is an AE. And then we have a 0. So AE plus a 0 is still AE. Then we have a 464, which is a 1D0, and an AE plus a 1D0, God, I hope this is right, is a 27E. And then a 928 is a 3A0, and then adding a 27E to a 3A0 gives us, in the end, a 061E. Yes. All right, so there's going to be some of the benchmarks, if you like, along the way. If I'm doing it correctly, I should see some of these appear in the registers. And basically my plan is to, even though it's probably not the most efficient, I'm just going to shift this thing each time I'm going to check all 8 bits, so there'll be a little bit of extra stuff at the end. But I've got an 8-bit number, which is 58, an 8-bit number, which is 27. I'll just keep shifting until there's no more multiplication to be done, and then each time I shift I'll have a look at this number. I'll keep a running total, which is these totals in decimal and these totals in hexadecimal, and hopefully that will work. All right, to the simulator. Right, so the first part of this is just to test to see if I can correctly identify the ones and zeros in the multiplying factor, and that is down here. So this is your 27 or 1b. So that's the binary representation, and if we're multiplying this by 58, which is 3a, then we want 3a multiplied when the 1 appears, and then we'll shift the 3a and we'll multiply it when the next one appears, and so on. So what I've got here is code which basically just loads up to 27, so we should see a 1b appear, and also says, let's test all 8 bits. So there's a counter there to test 8 bits. And then we'll roll R17 where 27 is to the right, and that should pop out this 1 into the carry flag. So we'll test that carry flag, and if a 1 does pop out, it'll go down here and subtract -1 immediately from register R16, which is clear. In other words, it'll count 1. The A tiny 13 doesn't have an add immediate, but if you subtract immediate -1, it's the same. If on the other hand it's a 0, it'll skip that step. It'll go down to here where there's a 0 partial, and it'll subtract the 1 bit from the counter, which is 8. So it'll go to 7. It'll test to see if it's it's equal to 0. If it's not, it'll go back up to test bits and roll the next one over. When it's finally finished, it'll jump to the top of the loop and start the whole process again. So let's assemble that, and then we will simulate, and we'll just step through this and see what happens. So firstly, we are initializing the stack, then we clear R16, then we load up, here it is, you can see it in yellow there, 1b or 27 into R17, and we load up 8 into R18, and then we're going to roll this to the right, and keep an eye on the carry flag up here. So there you go, so that kicks out that 1, so this becomes, there you go, so that becomes 0D, and you can see that there in R17. Then what we want to do is we're saying, okay, so that's a 1, so we want to actually subtract 1 from, or subtract a -1 from R16, in other words, add 1. And so when we step that, there you can see there 1 is added to R16, and then we subtract 1 because that's the first bit, so we're going to subtract 1 from R18, which is sitting on 8 at the moment. So there it goes to 7. Has it reached 0? No, so we will go back up to test the next bit. So now we're going to roll R17 again, so another 1 should pop out, so the carry flag should be 1. There it goes. Let's set it up on here, so this then becomes 6 is what we see, and then we will step through and say, okay, so another 1's popped out, so we add 1 here, counting the next bit. We're expecting 4 altogether because there are 4 ones in the original number, and then we subtract 1, so that's 2 bits tested, and we go back and do the next one. So then the next one pops out, and the carry flag hasn't changed this time because that is a 0. And now we have 3 represented here in R17 in line with this binary, and then we step through that, and we can see that no, it's jumped down to 0 partial, so it didn't do this line here, which means that we stay at 2 1s that we've counted so far. And we'll keep going through, and we drop this down there. We've tested 3 bits, so 8 drops down to 5. Is that 0? No. So we'll do the next bit, and we've rolled it over. So let's roll this over now. So that becomes just 1, and that's what's reflected in R17. And then we will test that bit. That is also a 1. So there you go, and it's 3 ones that we've counted so far in our 8 bits. And we'll subtract 1 more and test that. No, we're not at 0 yet. So roll the next one out. That is also a 1. So now we're down to 0. And if we step through that, we add that last one there. So we've got 4 ones altogether. And now we're just going to count down. We just keep rolling, it doesn't change. Just keep rolling, it doesn't change. All zeros now. And the last bit. And now we're down to all 8 bits tested. And so we jump to the top of the loop, clear R16, that's the 4 ones that we counted, and start the process again. So that would seem that we're able to do that part of the multiplication. Test each bit. The next bit is to find out if we can hit some of those other indicators that we were looking at on paper in terms of 58. So every time we roll over on this part of the code, we need to also double or shift 58 and then keep adding that to the running total. So let's try that. So the second part of this is to load 58. I'm going to load that up into register 21. I'm going to stick with doing this 8 times. So I'm still going to load my counter into R18. This time with test bits, what I'm going to do is I'm going to roll to the left R21 and R20, and you'll see the effect of this as we go through. Then I'm going to subtract my 1 from the counter, test to see if it's equal, and then if it isn't, go back up and do the next bit. Otherwise, go up to the top and start again. Alright, so we'll assemble that, and then we'll simulate, and here we go. So that's initializing our stack, and then clearing our registers. There's 58, which is 3A, and I've put the binary down here as well, which we'll keep track of. And then we load our counter into R18. Then we roll over R21, and you can see here that that's rolled over to be 74. We go back to our diagram, and there is the 74 here. So that's that first one where it's pushed over. So then let's see what that looks like. So a 0 comes in here, and we get rid of that there. So that's going to be a 7 on here for this nibble, and a 4 here. So that's where the 74 comes from. Very good. All right, let's keep going. So we will step, and we're going to be subtracting 1. So that's the first bit done, and that's not equal to 0. So we go back and do it again. So we'll roll 21 and roll 20, and we get E8. So that's going to be a roll here, and take 1 off at this end, and that is an E on this side and an 8 on this side on that nibble. Now that didn't appear on our image because you might recall that this shift here was all 0. But if that had been a 1 that we're multiplying it by, then that shift would have resulted in an E8. Okay, let's keep going. So step and subtract 1 and test. No, we're still good to go. And we'll roll R21, and there's a 1 that's appeared in R20. So what's happening here is that we're getting a 0 on this side, and we're pushing it out onto the other side. So I'll just leave that like that. So now we're getting our 1 here, and we're getting, on this side we've got our D, and here we've got our 0. Might separate this nibble out as well so we can see what's happening. Okay, all good. Let's keep stepping. So that subtracts 1, and test the bits. No, we'll do it again. Oh, did we get a 1D0? Let me just go to the diagram. Yeah, there's our 1D0. That's what we're expecting as we push that out. So there's our 4 zeros in a row there for our lower nibble. There's our upper nibble there at 1101, which is our D, and there's our 1 that's been pushed over into R20. All right, so then let's step, and we go to A0 and 3. So looking at that 3A0, here it is down there, 3A0. So that's working out beautifully, and that's our 4th rollover, and so on. Not much point keeping track anymore. These numbers didn't appear at all, but at least that's proof of concept that we can do that. Our next thing to do is to add what's appearing over here. Let's just restart that. So take it as an example. If we step through, that very first 3A needs to be added to our final result. So we might store that in the next 2 registers, so we've all got that on the one line. So let's code that up now. Right, so here's the final program. So we're going to be using all of these registers. So the first thing to do is to clear them out. Then I'm going to load 27 into R17 as per the first program that we did, and then I'm going to load 58 into R21 and load my counter into R18. Then I'm going to roll to the right the 27 and find out whether or not it's a 1. If it's a 0, then I skip down to this section here. If it is a 1, then I'm going to add whatever is in R21 to R23 and add with carry whatever is in R20 to R22. Then we roll to the left R21 and R20 as we've seen before, subtract our counter, test the counter, and do it again until we reach our 8 bits. So let's assemble that, and we'll simulate it. And what we're looking for is some of the numbers that we have seen when we did this by hand. So let's just step this through. So that's our stack initialized. It's clearing all of our registers to start the process. And here we go. So there's our 1B loaded and our 3A. So we certainly recognize those. There's our counter. And we roll over as we've seen before. And then we that's a 1 is our first bit out, so we add the 3A, so you can see 3A gets added out here to R23, nothing to R22 at the moment, and so that part is just here. Okay, so we've just got a 3A, which is eventually going to be added all the way through. So let's keep going now, and we've rolled this now to 74. So going back to our diagram, that's the 74. So that's good. That's worked well. And then we go to the next bit, and it is also a 1. So we're going to add the 74 to the 3A. So firstly, that produces an AE, and we go to our by hand here, and there's our AE, so that's working well. And we'll step through again now, and that rolls over to be an 0E8, but we don't end up using that one. But let's just see that one go through, because our next bit, when we roll over, hasn't activated the carry flag, so there's no addition. We keep rolling, and we end up with our 01D0. So we're down here, there's our 1D0, and we keep going, and our next bit pops out, and it's also a 1. So we need to add those together. We get our 027E. There's our 027E down here. So that's keeping our cumulative total going. And then we roll that over next. There's our 3A0. So that's our next one down here, 3A0, which will be adding to our 27E. So they're all set up now for our final answer. And we keep stepping. And it's a 1. So there's our 1E. And that's actually going to end up being our final answer because the rest of our bits are 0. But we'll keep going. And we just keep skipping that. And as I said, not very efficient. We'll go all the way through. We might fix that up eventually, but ultimately just, as I said, seeing it work the same as what we do by hand, testing that last bit. And we get down to 0, and we are finished with our answer here, 061E in our registers 22 and 23. So that's working now, and we know how to do 8-bit multiplication to produce a 16-bit answer. See you next time.